In this video, we will be taking a look at correlation. What exactly is correlation? Well, keep watching and find out. You will also find information in our book on correlation started on page 197. If you do not have the book, just continue with the video to find out all you need to know about correlation. We know some things are related. We also know that some things are not related. Researchers tend to be interested in those things that are related. For example, in medical science, there is a complex and modest relationships between diabetes and certain types of pancreatic cancer. Again, in medical science, there's a relationship between increased age and benign prostate cancer. In psychology, there's a relationship between parents and their children's intelligence scores. We could go on. Indeed, if we did, we would find a relationship between methane levels in the atmosphere and cow flatulence, and between McDonald's restaurants and methane levels. While cow flatulence may not be immediately of concern, certainly prostate or pancreatic issues might be. Knowing that relationships exist helps us take greater note of areas of concerns, such as cancer, or may point to possible relationships that allow for recognition of deviations from these relationships, such as parents and the intelligence of their offsprings. These relationships that we are talking about can be identified by a statistical procedure called correlation. The concept of correlation was developed by Sir Francis Galton, Charles Darwin's first cousin, with a paper presented on the topic of correlation in 1888. Correlations are usually presented as a relationship between variable x and variable y. This relationship was conceptualized by Galton, mathematically defined by J.D. Hamilton Dickerson, and later refined mathematically by Carl Pearson. Correlation relationships can be represented by a number between -1 and +1 with any number between, but no number larger than 1. When the correlation approaches +1, we can say the variable x and y move in the same direction together. That is, if x gets larger, y will tend to get larger as well. When the relationship is closer to -1, the opposite is true. X and y move in opposite directions. So as x gets larger, y would tend to get smaller, or if x is present, y is generally not, as in rain and sunshine. Besides the mathematical limitations just presented, meaningful correlation relationships utilize related data. That is, data locked together in some fashion, such as a particular x is tied to a particular y, as illustrated by these examples. While mathematically we could compare a correlation on random data, who would care? Another characteristic of correlation relationships is that they are not causal. You cannot say X causes Y. For example, there was a study that indicated that a rise in the stock market meant a rise in hemlines. Can we say the stock market caused hemlines to go higher? It would be a bit of a stretch to come up with some explanation for the relationship that has either logical or intuitive appeal. There are reasons correlations are not causal. First, there may be no appeal or intuitive connection, as in this sample. Second, is it a chicken and egg sort of thing? Is X related to Y, or is it the other way around? Y is related to X. And third, we do not have full control of extraneous variables. While one may randomly select on the variable X, once X is selected, Y is set and is not random. Correlation studies are most useful in helping researchers define the lay of the land, particularly in new research areas. For example, knowing a relationship exists between diabetes 2 and certain pancreatic cancers helps point the way for further, more definitive research to pinpoint why this relationship exists. We might say that correlation results alert us to areas that bear further investigation, just as highway signs direct us to our final destination. Thanks for watching, and please check out more of our YouTube videos for videos on statistics and research methodology.